I mentioned our last meeting change in scheduling, and I've got a hard copy that's available here. Since the governor has not announced Juneteenth as a holiday, we're gonna expand and reduce the workload that would be necessary to give that as a holiday. So today we're doing a review for Exam 3, Chapter 13. And next Tuesday, we'll have the exam on this material, plus Chapter 14, Acids and Bases. Then I don't have to squeeze in Chapter 15. We're going to do that on Thursday. And let's see, I don't have a lab on that day. Probably best that we skip next Thursday for a lab. We won't have a lab on that day. And we'll go to the following Thursday. And from that point on, things should be the same as they were in the previous schedule. And I think all the dates that are in Brightspace, due dates and things, I've looked those over and I think they're consistent with the new schedule. But as I always say, when in doubt, go back to the syllabus or the posted schedule. If there's a conflict, then Brightspace is in error. All right, let's take a look at, I've only got 22 highlighted here out of this review document. If there are any others that have given you pause, then we'll tackle those first, actually, if you have those in mind. Otherwise, I'll jump right in and we'll work these out. And as I go, if you think of something that just you forgot and it's come back to you, then stop me and we'll deal with it. Okay, I'm going to go down to number 2 for the first one. Which of the following is true for a system whose equilibrium constant is relatively small? When we look at the any reaction, this generic reaction, and we know how to write the mass action equation for the equilibrium of this reaction, and we're going to do it in terms of molarity, concentration. And we're assuming that all of these factors are either in solution or gases. If they're pure liquids or solids, you don't put them in the equation. For a simple reason, they don't change concentration during the process. Okay, so we put the reactants first in square brackets to designate molarity. And then their coefficients are the powers of each one. I'm going to all this details as a reminder. We can talk about it. All right, so if we say that the equilibrium constant is relatively small, how do you get a small value out of a quotient? There are one of two ways, or both. You either have a very large denominator or a very small numerator, or both, in which case you get a small quotient value for the K. What does that mean? That means that you have very little product and a whole lot of reactant. Okay, so if we look at our choices, A says it will take a short time to reach equilibrium. All right, first of all, time has nothing to do with equilibrium. Equilibrium could happen in milliseconds. It could happen in minutes, hours, days. It could take 1,000,000 years. We don't care. Not when we're talking equilibrium. We only want to know the beginning and the end, or the condition at which the rates are equal, forward and reverse. So we don't even consider A and B because they're introducing a time factor. So C and D are possibilities. equilibrium lies to the left. Okay, if it lies to the left, that means this is big and that's small. That's what we want. So C is the answer there. And you can't have two equal because the only two left are opposites. D is false. Now, if your instructor got sneaky and changed the wording, say the equilibrium constant is relatively large, it would be equilibrium lies to the right, because that would make this big and that small. And the quotient then would be a large number. Okay? It's really just simple math. That's number 2. Number 3. Excuse me. So we've got this equilibrium system where carbon dioxide and hydrogen gas yield carbon monoxide and water. And we're given the enthalpy for that reaction. Just looking at the reaction, we can tell that this reaction is endothermic because the delta H is positive. That may not be necessary to solving the problem, but it's true nevertheless. If K equals 1.6 at 1,260 K and 0.15 mole each of the reactants and products, all at that same temperature, were placed in a 1 liter thermally insulated vessel. So that means that the temperature doesn't. There's a problem with that question. If the vessel is thermally insulated and the process is endothermic, what's going to happen to the temperature? Temperature is going to go down, right? Let's write the equation up here, and I'll tell you what I mean by that. These are all gases, aren't they? Yeah. So every term is eligible for the equilibrium expression. Carbon monoxide, water. Well, the first question we have to ask ourselves is, is this equation balanced? Before you can do an equilibrium, you have to have a balanced equation. So let's see if it is. There's one carbon, there's a carbon. 2 oxygens, 1 there and 1 there, okay. 2 hydrogens, 2 there, okay. So the equation's balanced. We're good to go there. I'm going to go ahead and put the other information that we have here. K equals 1.6. Okay. And we might as well write the expression. We're probably going to need it anyway. So we have carbon monoxide to the first power, water to the first power, and then CO2 to the first power, and hydrogen to the first power. Okay, the other information we're given is a 1 liter container with 0.15 mole each. So what's the concentration? 0.15 molar, right? Moles per liter. So we have 0.15 molar for each one as an initial condition. So if we construct the ice table, that's where they will go. All right. The part of the statement that gives me pause is thermally insulated. Okay, to answer the question, I think we're going to have to assume that the temperature doesn't change. I mean, that's the only way we can solve the problem. Oh no, look at the answers, right? You guys were looking at the answers while I was gyrating, right? Yeah. What's going to happen to the temperature? Okay, so if it's endothermic and the vessel is insulated, which now it makes sense based upon the answers, where would that term go in this equation? Endothermic heats go on the reactant side. because they're being absorbed into the system as you produce products. So this would put the 42 kilojoules per mole on this side. Okay. So as it comes to equilibrium, what we need to know is which direction is it going to go? That's the important factor. So how do you calculate that? Since we're given reactants and products, and none of them are zero, we have to calculate the Q and compare it to the K. All right. So the Q would be that's simple. 0.15, 0.15, 0.15, 0.15 is 1, right? Yeah, the Q is 1. Okay, so if the Q is less than the K, which way is it going to move? If this is less than K, that means we don't have enough of this and too much of that. The Q is smaller than it should be, which means the numerator is too small. That means we don't have enough product. And the reaction is going to move this direction. Okay? So now we can say something about the temperature. If the reaction we know is going this direction, it's going to absorb heat, and the temperature should drop. So far, so good? Okay. To the right, toward products, because this is too small. That means this is not big enough. We don't have enough product. So we're going to move to the right, absorb energy, the temperature will decrease. So the only ones that are eligible on that count are A and B. Temperature would decrease. But why? Well, not why, but what else? And the mass of CO2 would increase or decrease. This would have to decrease as we go that direction. Yep. So B should be the answer. Now, how did I know to do that? Because of the answers. The question had to do with temperature. So in order to analyze the effect on temperature, we had to know which way the reaction was going to go. And from there, I worked backwards to comparisons here. Okay? All right. Okay, who's next? Number 4. Given this equation, we're going to use that equation and the other information to go through 4, 5, and 6. We might look at 5 while we're here too. I don't have it highlighted, but it might pay to do that. So the equation we're working off of is 2A gas. 4, 5, 6. So we've got 2A and the gas yields what? They go both directions. 2B as a gas plus C. And at a particular temperature, the K is 1.6 times 10 to the 4th. K equals 1.6. 6 times 10 to the 4th. Okay. What does that K tell us? That tells us at this temperature, once it reaches equilibrium, we're going to be predominantly product. Okay. So we'll keep that in mind as we look at each one of these. So 4 says addition of chemical B to the mixture will do what? If we put B in here and it's at equilibrium, well, Chatelier says it's going that direction. So it would cause A to increase. Yeah. Well, we got cannot be determined as stupid. None of the above, we found one that works. So it's not D or E. And B says C would increase. That's going the wrong direction. Had no effect is irrelevant also. So this one is A, would give us the correct answer. Let's see. Well, since I've got 6 highlighted, let's go to 6 first, and then we'll come back to 5. Raising the pressure by lowering the volume. So all of these are gases. Will changing the pressure have an effect here? Maybe, possibly. What else do we need to know? We need to know the stoichiometry. 2 moles on this side, 3 moles of gas on this side. So if we raise the pressure by lowering the volume, we lower the volume, the response of the system is going to try to make fewer molecules. So it's going to go from this side to that side as we decrease the volume. So we're moving from right to left as this is written, which means what? A to increase? Yep. That's what it'll do. B won't increase, A will increase. So A again. Now let's look at B. At a higher temperature, K is 1.8 times 10 to the minus 5. So this is at T1, at T2, which is greater than T1. We've increased the temperature. Now K2 is negative 1.8 times 10 to the minus 5. So at this higher temperature, we are decreasing the value of K. So what does that mean? If the K is very small, that means now we're favoring reactants. Right? We're not making any product at a higher temperature. So what does that say? If we increase the temperature, which side should it go on to make it shift this direction? It has to go over here, doesn't it? Yeah, if we put enthalpy on this side, then if we increase the temperature, it's going to drive this reaction back here and make this one very small. So this is an exothermic reaction because the delta H is on the product side. Okay, so what will it do to the concentrations? Well, it will increase A and decrease B and C. Now that's not working. At a higher temperature. Oh, I didn't read the rest of the question. And you guys are just sitting there watching me fumble around. That's not special. It happens in every class. Okay, what else? Placing the equilibrium mixture in an ice bath, thus lowering the temperature. Okay, at this higher temperature, now we're at equilibrium again. And we put it in an ice bath. Now, which way is it going to shift? Let's go that way. Because we're removing this term and it's shifting that way. Okay, now B makes sense. We're going to increase the concentration of B at that higher temperature. I was making up my own question, right? Instead of reading the one that was there. So that means B is the correct answer as it's given. Let's stop at number 8. We got pink and blue. So we're working off of this equation where we have, let's see if I get my names correct. Hexahydro cobalt 2 complex ion. This one, 6 waters associated with that, and it's 2+ ion. This is a complex ion, and these are all in aqueous solution. We didn't write it in there, but it's true. And then we add chloride ion 4 of them. That's in equilibrium. Oh, this is pink. So you can actually track the reaction. And this is a different complex ion with chloride now instead of water. This is aqueous. And the water ends up over here. This is blue. Okay. All right. When cobalt-2 chloride is added to pure water, the cobalt-2 is hydrated, gives you this complex ion. That's not right. It should be C. The hydrated form then reacts with chloride ions to set up the equilibrium shown here. So we put this cobalt in solution as the chloride. Cobalt reacts with water and gives you that ion and releases these chloride ions. But it also creates a complex ion with chloride. Now that's in equilibrium. And all we had to do was add cobalt chloride to water and automatically sets up that reaction. Okay. Now, if the we just look at it, since water is very plentiful, and this is probably like that. If it's an aqueous solution, that's a pure liquid, and the equilibrium expression, if we were to write it, would not include water. Okay. So the question is, which statement below describes the change that the system will undergo if hydrochloric acid is added? If we add HCl, what are we adding? Chloride ions, right? So which way will it shift? To the right. So if it were pink and we put enough of them in there, we'd now be blue. Let's see. A says it should become more blue. Yeah, A is right. That's true, correct. B, C, D, E. So A is correct. Should become more pink. You can't have it both ways. Nice. The equilibrium will shift to the right. Yes, that's true. That one's wrong. And D says the equilibrium shift to the left. Again, you can't have both. And E says 2 of the above. So E is the answer. Let's see. New equation. We're going to look at complex ions in a subsequent chapter. Actually do a lab with also. Oh, excuse me. Consider this equilibrium 2 hydrogens, number 9. Let's see. 10 is based on that one also. 9, and maybe we'll take a look at 10. I think we got enough time. So we're based this on 2 hydrogens plus that one. Yes. Excuse me. And this yields 2H2X. 2H2X as a gas. Okay. So number 9 says, if this system is at equilibrium, addition of X2 to the system will cause what? H2 to decrease? Yeah. We add some of this, it'll react with some of that and reestablish the equilibrium further to the right. The equilibrium position will shift to the right. It won't cause X2 to decrease. X2 will actually increase. It won't increase by the same amount that you added because you're going to consume some of it. But it will increase compared to the original equilibrium concentration. So X2 will not decrease. H2X will not decrease. Have no effect, cannot possibly kill. Okay. We ran out of choices. So A is correct for this one. You will get an increase, a decrease in hydrogen. What happens to D? Addition of argon to the above equilibrium. If that's going to do what? It's going to increase the pressure according to Avogadro. But will it have an effect on the reaction? Nope. Because argon's inert. It's not it's not a gas in that group. If we change the pressure by, in fact, we did change the pressure. If you add X2 as a gas, it increases the pressure. So you could look at it two different ways. Increasing the pressure goes from 3 to 2. But increasing the concentration also goes to the right. Both ways work. But when we add argon is a gas and it changes the pressure, but it does not increase the frequency of collisions or the reactants or the decomposition of the product in the opposite direction because it's not part of the reaction stoichiometry. Okay, so it will have no effect. Addition of argon has no effect on this reaction. For 11. Which of the following statements is true? Okay. When two opposing processes are proceeding at identical rates, the system is at equilibrium. Yeah. And that goes for any system. It doesn't have to be chemical equilibrium. If the rates forward and reverse are in balance, then your system is at equilibrium. That one's true. Now, are there any wonky ones in there? None of the above is true. E, so that can't be it because we found one that was true. And there are no two of the aboves, so we're done. We can look at the others for fun. Catalysts are an effective means of changing the position of an equilibrium. Is that true? No. Catalysts just change the rate. The equilibrium, you just get there faster. Concentration of the products equals that of the reactants and is constant at equilibrium. No, they're talking about equilibrium position. And the equilibrium position can be acquired. You can get to the equilibrium position with any number of concentrations. It's the law of mass action that determines equilibrium. That's the constant. But the position can be, the sky's the limit. An endothermic reaction shifts toward reactants when heat is added to the reaction. Endothermic puts it on the left-hand side. So if you heat it up, you're going to shift to the products. Right? So D is false also. All right, let's see. How about 14? Consider the reaction represented by the equation. SO2, sulfur dioxide, plus oxygen, was it? Yep. Plus oxygen gas is in equilibrium with SO3. Now let's see, that balanced 2 sulfurs, 4, 5, 6 oxygens. Yep, we're good. Okay, next step. Systems at equilibrium. Which of the following explains what happens after the addition of oxygen gas? Assume constant temperature. Okay, we don't have any. We would expect, since this is a combustion, it's probably exothermic. But that's why we're told that this assume constant temperature. So if we, let's see, what was it again? Addition of oxygen. So we're going to add oxygen. So we should shift to the right. Yeah, SO3 increases. So out of our selections, A is a possibility, and D, the amount of SO3, no, E, right? SO3 increases. So these are two possibilities. There's more to the statements. So the value of K increases for this one. K increases, and probably E stays the same. Same. Okay. The key there is the temperature is constant. If the temperature doesn't change, the K doesn't change. That's why E is the best answer. We don't change the K when we change concentrations. Okay, it took me 5 minutes to do that. When you're taking a test, that's probably going to happen in 15 seconds at most, if you know the material. But I take all that time to explain it in detail. Okay, let's see. 15. There we go. 15 is based upon this equation. So we've got bromine chloride as a gas is in equilibrium with bromine gas and probably chlorine gas. Right? Yep. Okay. What would be the effect on equilibrium for, okay, we got A and B. So A says change the volume at constant temperature. Changing the volume at constant temperature. It doesn't say which direction the volume goes. Okay. Change volume at constant temperature. Okay. And B says increase the temperature at constant volume. Increase temperature, constant volume. Okay. So what happens if we change the volume? Well, we've got 2 moles here, right? And we've got 2 moles there. Right? Change the volume, nothing happens at constant temperature. Right? So which one is equilibrium shifts? No, for A, no change in equilibrium. So that's D or E. Now, which one of those applies to increased temperature at constant volume? Increase the temperature. I don't know. Shifts toward products or shift toward reactants? It doesn't tell. Oh, it does tell us. It's endothermic, right? Okay, increased temperature, you're going to shift toward products. So that's D. It helps to read the whole question. Let's see, which next one I thought was important. How about 20? Now, if I'm skipping any that you need to deal with, stop me. The following reaction is allowed to reach equilibrium in a glass bulb at a given temperature. Okay, the mass of the mercury 2 oxide in the bulb could be increased by. All right, so we've got 2H2O solid and solid decomposes into mercury liquid plus oxygen gas. Okay, and the heat is positive. Yeah, so the delta H is going to go over here. Okay, what would the equilibrium expression look like? That's it. Because we got solid and liquid in there. They don't count. So it's just that concentration of oxygen. So the mass of HGO in the bulb could be increased by. We could increase this amount by what? Well, we could add oxygen, right? If we added oxygen, we'd shift it back over here. What if we added mercury? We're not changing the concentration of mercury, so it has no effect. What about pressure? What if we decreased the volume? It would try to compensate by reducing the amount of gas, wouldn't it? So if we increase the pressure by decreasing the volume, we would shift to this side. Okay. Add that or increase pressure, which is decrease volume. Either one of those would shift back this direction. So what are our choices? Removing some Hg. No, that doesn't change the mercury concentration, right? So A can't be hit. B, C, D, and E. So that one's out. Reducing the volume of the bulb. Oh, yeah, B works. B works. Adding more mercury. No, that won't work. Increasing the temperature. If you increase the temperature, you're going to shift it the wrong direction, aren't you? Yeah, you're going to add this term, which shifts that way. And so that one doesn't work. And removing some O2 will go also to the right. So B is the only good answer out of that bunch. '21. At 500 K, 1 mole of gaseous ONCl is placed in a 1 liter container. So its initial concentration is 1 molar, right? 1 mole per liter. At equilibrium, it is 5.3% dissociated according to the equation shown here. Determine the equilibrium constant. Okay, so here's the balanced equation. 2ONL. These are all gases. You have to assume that. Or does it say that? Yeah, it says gases. We know that nitrogen monoxide is a gas and chlorine's a gas. And they appear to be balanced. Yep. Let's see. So we're not changing the temperature. We want to know the equilibrium constant. So the equilibrium constant, since they're all gases, the equilibrium constant, and we're given the initial amount is 1 molar. Let's see how many decimals do I get? Doesn't say. Like many as I want, I guess. And nothing here and nothing here. But the K is going to be concentration of NO squared, concentration of CO2, first power, and concentration of ONL squared. What we need to know is what are the equilibrium concentrations. So there's going to be a change. Then we're going to end up at equilibrium. Which way we're going to shift? To the right. Right? We're going to go to the right. So we're going to lose some here and gain some there. But we're also told that the equilibrium, at equilibrium, 5.3% dissociated. That means this has been reduced by 5.3%. 5.3% of 1 is 0.053, right? We lose that much percent. That's 5.3 per 100. right? So since we only have one, then we reduce this 2 to the left and 2 to the left. That gives us 0.053. That's where I got that number. So we've lost that much. Well, the ratio is 2 to 2 and 2 to 1. Right? So we would have 0.053 added here, but only half that much would be added there. 2. Okay, so now we can calculate the values that go into the equation. Let's see, 1 minus 0.053 is 0.947 molar. This is 0.053 molar, and this is 0.053 divided by 2, which is 2.65 times 10 to the minus 2 molar. Now we can calculate the value. We just have to plug them in now. Does anybody have any trouble with how I got to that point? Probably the first thing that's going to throw you is how I got this. Okay, and then we had to calculate what's the final concentration. Okay, the change is pivotal to this problem. Only when it's stated that way. It says 1 mole of ONCl was placed in a 1 liter container, sealed, and it comes to equilibrium. That means when you put that in there, there's none of that to start with. That's why this initial. Yeah. Okay, now we can throw these numbers in here. NO, 0.053 squared, and then 2.65 times 10 to the minus 2 to the first power, and 0.947 squared. Well, that should give us our K. 0.053 squared, and then 2.65 here times. So I get 7.44 times 10 to the minus 5 up here. And I'm going to divide by 0.947. I'm going to square it first, then divide. So I get, let's keep a couple of, maybe 8.30 times 10 to the minus 5. Okay. Best answer for that one is A. Yeah, like I said during the lecture, this learning how to use the ICE table is important because we're going to use it for the rest of the semester. We might be on a different topic, but ICE is still there and we're going to use it. Okay. '24. Let's see. Nitrogen gas reacts with hydrogen gas to form ammonia. Oh, our old familiar Auerbach. Nitrogen gas reacts with hydrogen gas to produce ammonia. Okay. Before we go any further, that equation is not balanced. We've got 2 nitrogens over here. We need 2 there. That means we need 6 hydrogens. Now we're balanced. Let's see. At 200 degrees in a closed container, 1 atmosphere of nitrogen gas, 1 atmosphere. Let's see how many decimals do I get? Just 4. 1 atmosphere is placed in the container with 2 atmospheres of hydrogen. Okay. At equilibrium, the total pressure is 2.2 atmospheres. So P total equals 2.2. 2.2 atmospheres, which is equal to what? It's the partial pressure of nitrogen plus the partial pressure of hydrogen plus the partial pressure of ammonia. Right? If there's any of these left, there will be some of this left, this left, this left. That's the total pressure. According to Dalton. Okay. What else are we given? Calculate the partial pressure of hydrogen gas at equilibrium. Okay. So there's going to be some change, and we don't have that in the beginning, so we know it's going to shift that way, right? All right. So we're going to lose some hydrogen, we're going to lose some nitrogen, and we're going to add some ammonia. So if we want to know the partial pressure of hydrogen, I would suggest making your unknown, your X. Well, actually, usually what I try to do is make the unknown equal to the end product. But now we're talking about losing some of this as maybe X, but it's going to give us a calculation down here anyway. So I think it would be easier to make X the one that's a single unit in size, like this one. Then this one would be a loss of 3 times, and this would be a gain of 2 times X. So I think that would be easier. So if we lose an X here, we have to lose 3 X's here. And we're going to gain 2 X's here. Right? Okay. So now we have 1 minus X for the equilibrium of nitrogen. We have 2 minus 3X for the hydrogen equilibrium. And we have 2X for the ammonia. Those are partial pressures because we started with partial pressures here. Okay? So if the total pressure is 2.2 atmospheres, then 2.2 atmospheres is equal to nitrogen plus hydrogen plus ammonia. So there we have an equation in one unknown. Okay? That's probably the trick. How did I get there? This is at equilibrium, and this is at equilibrium, so that must be equal to the sum of all those. Okay? So to solve this, we just say, okay, this is plus and plus, so we just take the numbers, like 1, 2, 1 plus 2 plus 2 is 5, right? And then we have a minus X. That makes a minus 4X, and, oh, excuse me. That's not right. That's 2X. This is 3 for the numbers, right? And then the X's. So this is 2X, and this is minus 3, and minus 4X. That's minus 2X, correct? Okay. That's equal to 2.2. Now we put, I'm going to move this over here and move that one over there, just so I can get rid of that negative sign. So this is 2X equals 3 minus 2.2. Right? Okay. So this is equal to 0.8. Yeah, 0.8. That means X equals to 0.4 atmospheres. Now they want to know what hydrogen is. Well, hydrogen we have to calculate from this expression right here. So this is 2 minus 3 times 0.4. Right? So that's 2 minus 1.2, which is 0.8, right? Can you do that in your head? It helps to practice that type of stuff, calculations in your head when you can. I don't know, it keeps the neurons firing. So this is 2 minus 1.2 is 0.8 atmosphere for hydrogen. Okay, that's B. All right. If there are no questions, we'll move on down the road. And this seems really complicated on the surface, but if you understand, if you've mastered what the ice table does and what equilibrium means, and you pull in some things from the past, like Dalton's law of partial pressure, then it's not really that difficult problem. It's just you have to slow down, break it into pieces. 25. Initially, 2 moles of, oh, here's another Haber thing, nitrogen and hydrogen. Okay, I got to go back to this one. Nitrogen, hydrogen. Reconstruct ammonia. This is 2 and this is 3. Okay, now 2 moles of nitrogen and 4 moles of hydrogen in a 1 liter container. So that's 2 molar for nitrogen and 4 molar for hydrogen. This is initial. 2 molar and what did I say, 3? No, 4. This is 4 molar because it's in a 1 liter container. Let's see. Oh, and they balanced the equation for you. I switched nitrogen and hydrogen there. Equilibrium concentration of ammonia is 0.55 molar at 700 degrees. So 0.55 molar at equilibrium. Okay. The value of K for this formation of ammonia is. All right. So if we started off with 0, how did we get here? We had to add 0.55 molar, didn't we? Where did it come from? Well, it came from this side. So what's on this side? Well, the ratio is 1 to 2. So half nitrogen is required to make that. So we would have 0.55 divided by 2 is negative. And if this is 1 and that's 3, then we would say 3 times 0.55 divided by 2 is lost from hydrogen. Okay. Now let's see. I'm not going to try to do that again. This one is 0.275. Oh, excuse me. That's 0.275 subtracted from 2. Now this is 1.725, and I'm going to hang on to my decimal points to avoid rounding error. And this one is 3 times that one. So 0.55, 3 times that divided by 2 is 0.825 subtracted from 4. And this is 3.175. There we go. So we can calculate the K now. This would be ammonia to the second power over nitrogen to the first power and hydrogen to the third power. So we put ammonia in here as 0.55 squared. And then nitrogen is 1.725. And hydrogen is 3.75 cubed. Now the rest is number crunching. What happened? Somebody left. Okay, so 0.55 and square that, and then 1.725, divide that into it, and 3.175, and cube that one. So let's see how I would do here, divide that in. So I get two significant figures. 5.5 times 10 to the minus 3. That would be C. Okay. Just takes practice. Okay. 26. Or you still right? Good. Okay. We'll go to 26 next. And 26, first glance, looks like it's combining equations to get the K for the overall equation. It's kind of like Hess's law, only with equilibrium. Oh, there's Kaylee again. Okay. Madison, they must be on their way. Michael sent me an email and said that he was going to have to drop the class. Yeah. He hasn't dropped yet. Yeah. He said he's working 2 jobs and some other things happen. So
we feel that. Yeah, we both work 2 jobs.
yeah.
Yeah.
I told Morgan that the other day, yesterday, in fact, that I had gotten that message from him and it might be good for her to contact him and see what the situation is. Yeah.
Because you can take chemistry while in the program too. She said she wouldn't recommend it.
Yeah, it's pretty intense.
Maybe anatomy or something like that, but not. Yeah.
Well, we've been wishing the best of luck. Let's see. We've got these equations. 26. These equations, 4C solid, 4. My brain in neutral. This is a solid plus oxygen, gas, yield, 2Cu2O solid. 2 solid. And K1 for this one is just K1. This is hypothetical. Let's see. The other equation that we're going to put together to give us the overall is 2CuO solid. 2CuO solid yields Cu2O solid plus 1/2 O2, and this one has a K2. Okay, what's our target? I should have put the target up there first. The target, we want to combine these to give us 2Cu solid plus O2 yields, this is gas, yields 2CuO, 2CuO. So what we want to know here is the overall in terms of K1 and K2. Okay. So what do we have to do to each one of these to get it right? 2 CuOs need to go on this side, on the right-hand side. So this equation has to be inverted. Right? We need Cu2O solid plus 1/2 O2 gas yields 2 CuO solid. Okay. So what does that do to the K value for this one? When you invert an equation, you invert the K. So the K on this one will be K to the minus 1. It's the inverse. Let's see. The answer's got no minus ones in there. So let's write it in standard notation. This will be 1 over K1. Okay. We're going to use this one, and we've got that covered here. Oh, excuse me. Wrong one. That covered here. Okay. No, I got the wrong one. That's K2, people. Because I was inverting this equation. Okay. What else do we need? We need oxygen on this side and 2 coppers on the side. Well, there are 4 coppers here and 1 oxygen. So if we take half of that, right? Half of that will give us one of these and one of these and one of those. Did I write that one correctly? CU2. If we take half of this one, that gives us 2 coppers. Okay. That gives us a half O2. And then on this side, it gives us 1 Cu2O. Correct? Okay. Oh, that'll work. What's the K? If you multiply your equation by any factor, that becomes the exponent of the K to give you the revised K. So that would be K1 to the 1/2 power, because that was our multiplier. Okay. Now let's see if it adds up. Let's see, we got the copper here. We got 2 oxygens, 2 halves of an oxygen, which makes 1 whole. That's good. And then when we add these together, this one cancels that one and leaves us these guys. So we're good. Now we can calculate the K. So how do you do the K for the combination? You multiply all the K's together. So the K for the overall reaction is going to be equal to K1 to the 1/2 times 1 over K2. So that's K1 to the 1/2 divided by K2. That looks like E. Okay. No response. I'll go to the next one. So once you guys start your program in the fall, are you going to quit your jobs? No. Okay. I just wondered. Yeah. If they're going to be able to, you're going to be able to work around your jobs to do the program. That would be better. Yeah. Okay. Let's see. That was, now we're up 28. Let's see. I better check the time here. A little after 10. Okay. Yeah, we're good. Let's see. Exactly 1 mole of N2O4 is placed in an empty 1 liter container. That means its initial concentration is 1 molar. Allowed to reach equilibrium, as described by this equation. Okay, so we got this N2O4 which decomposes to 2NO2. Right? Yep. Okay. And the initial concentration here is 1 molar, because it's 1 mole in a liter container. And we don't have any O2 to start with, NO2. All right, if at equilibrium, the N2O4 is 37% dissociated. Deja vu. We've seen this kind of problem before, haven't we? If it's 37% dissociated, we're going to lose 37% of that. Right? So that means we have 0.63 once we reach equilibrium. And since it's 2 to 1, we're actually going to add 0.74. Hmm? 0.7. Okay. Now what's the question? What is the value of the equilibrium constant? Okay. So AEQ is equal to NO2 squared over N2O4. So we've got 0.74 squared over 0.63. Should be simple enough. 0.74 squared share. So I get 0.87. That's E. Let's see, I don't need that again, do I? No. $29. Go. Consider this reaction. Hydrogen, which is a gas. Now, does it matter? At high temperature. Okay, at high temperature, iodine is also going to be a gas. And the product will also be a gas. I think that's important. Because at room temperature and pressure, iodine is a solid. And the K is 44.8 at high temperature. Okay. If equimolar mixture of reactants gives the concentration of the product to be 0.5 molar at equilibrium, determine the equilibrium concentration of hydrogen. All right. Let's see. Are there any assumptions here that we have to make? Equimolar mixture. That just means we have the same molarity of this one and this one. But this one is 0. And the product is 0.5 molar. 0.5. That's useful. How did it get there? It had to be here. Like that, right? So if this is equal to this, and we lose, that's 2. So we had to lose one of these. If this is 2, then 1 is 0.25, correct? That was 0.25. So x minus 0.25 and x minus 0.25. So there's and one unknown. That should work. So 44.8 is equal to HI squared divided by H2 over I2. Okay, so let's put our values in there. HI is 0.5 molar squared divided by X minus 0.25 times X minus 0.25, and that's just squaring it, correct? So the nice thing about this is we don't have to worry about a quadratic because the numerator is squared, the denominator is squared. So we can say this, 0.50 divided by X minus 0.25, the whole thing squared. That's equal to 44.8. Now we can take square root of both sides. Okay, 44.8, take the square root, and that's 6.69. 6.69. We're going to take the square root of this side, take the square root of this side. That's what I just did. That means this is going to be 0.50 over X minus 0.25. So now I have to bring that over here, which is 6.69X minus a quarter of 6.69. This is 0.99. And that's equal to 0.50. Now I can put this on the other side. 6.69x equals 0.5 plus 0.999. That's 1.4 x equals this divided by 6.69, which is 0.224. That's x. The question was, though, determine the equilibrium constant. Wait a minute. Concentration, excuse me. Concentration of hydrogen. Okay, so it's this minus that. That's not right. It can't be because the minus is bigger than the x. Oh. I'm making this thing harder than it needs to be. This is equal to hydrogen, x minus 0.25. There's the concentration of hydrogen right there, isn't it? So if I just move this over here, x minus 0.25, that's equal to the concentration of hydrogen, and that's equal to 0.50 divided by 6.69. Are we okay? I'm just taking, the question was, what's this concentration? And there it is right there. So I don't even have to solve for x because this is equal to the hydrogen concentration. So all I have to do is move this over here, move that over here, and divide 0.5 divided by 6.69. Do that again. 6.6. Yeah, there we go. So this is 7.5 times 10 to the minus 2 molar. There it is. That one almost slipped by me. Well, the only thing that stopped me was I got an answer that wasn't real. It couldn't happen. All right, 29, 30. Consider the following reaction. Given 1 mole of HF, 0.362 moles of and 0.7 moles of F2 are mixed in a 5-liter flask. What's the reaction quotient? Oh, this is simple. I'm gonna write the Q expression just from what's on the board. So Q here is going to be, assuming that's balanced. Let's see. Yeah, that's balanced equation. So we got F2 here to the first power, H2 to the first power, and then the denominator is reactants. This is HF squared. So all we have to do is insert the concentrations. Well, we got 1 mole of HF down here, but it's in a 5-liter container, right? Yep. And 0.362 moles of H2, 0.362, also in a 5-liter container to the first power. And 0.75 mole of F2. In a 5-liter container. So this is mole per liter. Mole per liter. Mole per liter. Okay. We write it that way, we can do the whole calculation, all of that together at one time. 0.75 divided by 5, and then 0.362 divided by 5, and times those. So the numerator is 1.086 times 10 to the minus 2. Divided by, what's 1 divided by 5? 0.2, isn't it? 0.2 squared. So that's 4 times 10 to the minus 2. And then we just divide those two. Divide. I get 0.272. I mark that. That's B. That's the Q. Now, are we given the K? We're not given the K, so we can't say anything about which way it's going to move. But that's the Q. If you have the K, then you can say, all right, as written, the equation is going to go this way or that way. The equilibrium will go right or left. But we don't have the K, so we can't say that. 31. Following system, 2NO2 yields 2NO plus O2. If the Kp value is 0.64, find the equilibrium pressure of O2 if the NO2 gas pressure is 0.52 atmospheres and the P is 0.3 at equilibrium. Okay, I'm going to put this equation on the board. 2NO2 gas decomposes. I should have put a double barbed arrow in there. This is going to be in equilibrium with those products. Okay. Kp equals 0.64, 604. So how did we get to that one, to that Kp? We got there by partial pressure of NO squared times partial pressure of O2 to the first power. And then partial pressure of NO2 to the second power. So that's the expression in terms of partial pressures. All right, now what are we given? Let's see. We want the equilibrium pressure of O2. We want this one right here. Equilibrium pressure of O2. If NO2 gas pressure is, at equilibrium. So we're told what these values are. 0.52 atmospheres of NO2. 0.52 atmospheres. And NO is 0.3. Well, this is easier than I thought it would be. So now we know that 0.604, oops, it's not going to work. 604 is equal to, we're given NO, yes, 0.3 atmospheres squared. And PO2 to the first power is our unknown. And this one is 0.520 squared. Now we've got an equation in one unknown. Should be simple. So I'm going to put 0.604 in there first. Punch it in right. And then I'm going to square this one because I want to bring it over here and multiply it by that one. 0.52, square it, and then multiply. Okay. Then I want to bring this one over here because this one's in the numerator. I'm going to leave it there. Square that one and bring it over here. So what's 0.3 squared? 0.09, right? Yeah, 0.09. And I'm going to divide that into the product that I got from the previous one. So this is PO2 equals 1.81 atmosphere. Okay. I thought it was going to be over. Silly me. All right, 32. Let's see what 32 does. Probably why I only had, 21 highlighted. Because there's so many, you have to work out problems. You don't just memorize answers. Carbon disulfide plus chlorine gas yields disulfur dichloride and carbon tetrachloride. Okay, I have a feeling we're going to need the equation up here. CS2 gas plus yeah, 3 chlorine and then equilibrium with is 2 plus carbon tetrachloride. They're all gases. Okay. So 2.14 moles of CS2, 5.85 moles of Cl2 are placed in a 2-liter container, allowed to come to equilibrium. So the initial concentrations would be 2.14 moles in 2 liters. 2.14 moles per 2 liter. That's initial. And chlorine is 5.85. Also in 2 liters. Okay. Found to contain 0.620 moles of carbon tetrachloride. So we're found to have 0.620 moles per 2 liter at equilibrium. How many moles of Cl2 are present at equilibrium? Okay. That should be fairly simple. Let me see if there's a quicker way to do this. Everything's in the same size container. I'll work it two different ways. Let's do it the kosher way where we have concentrations. All right. So this would be 1.07. This is 1.07 molar. And this is 293 rounded off molar. Okay. This is 0 and this is 0. So how did we get to this one? Well, we had to add 0.310 molar to do that, because this is equal to 0.3 molar. Okay. Stoichiometry says that we're going to lose that same amount, minus 0.310 molar. And chloride, we're going to lose 3 times that amount. So that's minus 0.930 molar we're losing. Okay. The question is chlorine. How much chlorine is left over? Well, let's see. 0.93 from 2.93 would be 2, right? 2 molar. And in 2 liters, that means times 2 liters equals 4 moles. Now, why did I get the wrong answer? Oh, 3.99, rounded off. Now, the other way I was thinking of doing it is, instead of concentration, what if we do it using absolute amounts? Just use stoichiometry. Will that work? Let's see. Okay, has everybody got that? Okay. So let's go back and do it stoichiometry. Since the size of the vessel did not change, then what's actually changing is the moles of reactants and products. So let's take out the volumes. Since the volume's the same for everybody, just take out the volumes. That, and that's what we had left, right? 620, yep. And do that. The reason I'm doing this is because this is a technique that we're going to use to manage the data that comes out of our lab that we're going to do today. Working with absolutes rather than concentrations. Recognizing that it's all based upon concentration, but it's easier sometimes to get to the answer going with absolute amounts first. So in this case, if we got that one, that means we had to 0.620 mole here. That means we lost minus 0.620 moles here, and a third of that minus 3 times that, excuse me. 3 times that. Minus, because it's 1 to 3. Minus 3 times that is 1.84, correct? Nope, 1.86. Sorry. 3 times 2 is 6. All right. Now let's subtract that and see what we get. 6 from 15 is 9. 8 from 17 is 9. And 1 from 4 is 3. Works both ways. Nobody's amazed. All right. Scroll to 33. Let's see, at minus 80 degrees Celsius, K for the reaction, N2O4, N2O4, yep, gas, an equilibrium with 2NO2 gas. And this is at temperature equals minus 80 degrees C. And the K for this reaction is 4.66 times 10 to the minus 8, which means at that temperature, it's pretty much staying over here. Okay, we introduce 0.47 moles of N2O4 in a 1 liter vessel. 0.047 moles per liter. Okay. And let the equilibrium be established. The total pressure in the system at equilibrium will be. All right. So we know that if we just introduced it, initially it's nothing. So let's find out what this concentration is first. So I think we're going to have to stick with concentration for this problem. Oh, duh. 0.047 molar, because it's in 1 liter. Okay, so the change is going to give us some NO2, right? Change is going to be, say, let's say 2x plus 2x. That means this loses 1x, but it's 1 to 2. Okay, and at equilibrium, you know what? This tells me that there's not going to be much of that over there. I think we can round it off. We can estimate that this is going to be the total molarity of gases in that vessel. See what I'm getting at? Save us the trouble of doing this calculation, because this is so small, there's hardly any of that going to be produced. So we've got actually 0.047 moles of gas. Right? That's N. Let's see. So how are we going to find out what the pressure is? There you go. We're going to solve for pressure. Equals nRT over V. We know what the moles are. We know what R is. Liter atmosphere per mole. Okay. Temperature is equal to minus 80 plus 273. Right? So that's going to be 273, 193. 193. And volume. What's the volume? Volume is 1 liter. So let's plug our values in. 0.047, 0.08206, 193 for the temperature, and volume is 1 liter. Okay. 0.047, 0.08206, and 193. And that is 0.744 atmospheres. There it is. I reduced the workload by recognizing this fact. There's not going to be so much of this produced, hardly any. So we can work off the original gas concentration. Nobody's amazed again. It's disappointing. I thought I was having a flash of brilliance. Okay. Um, let's see. 34. Getting close to the end. Oh, you can't tell. Four. Yeah. I got one more after this one that I've highlighted. Okay. A sample of solid ammonium nitrate was placed in an evacuated container and then heated so that it decomposed explosively according to the following equation. Okay. Do that. Hopefully use a very small amount. This is solid. And we're going to have N2O gas plus 2H2O gas. Okay. At equilibrium, the total pressure in the container was found to be 2.63 atmospheres. So total pressure, 2.63 atmospheres, is equal to the partial pressure. If it decomposed explosively, there's none of this left. So we can assume it doesn't take any of the volume. This is N2O plus H2O. Okay. Total pressure 263 at 500 degrees. So I don't know if that matters right now, but it's 500 degrees C. Calculate KP. Okay, so the KP here, let's see, I better not put it there. Put it over here. KP is going to be, since this doesn't count, it's a solid. That one times water squared. No, sorry. That's not KP, that's KEQ. KP is equal to the partial pressure of N2O times the partial pressure of H2O squared. There we go. All right. So when this decomposes, it doesn't matter what we started with because we already know what the outcome is. What's the relationship of this one to this one? Well, for every one of these, you get two of those, right? So if we say the partial pressure of N2O is a certain value, water is going to be twice the pressure, right? Because Avogadro says if you increase the number of moles, you increase the pressure by the same factor. So we can equate this one right here. That's equal to 2P(N2O). Right? And we're going to square it. So now we only have one variable. And if we put that into this equation, 2.63 equals P(N2O) times 2 P(2O). Right? So this is going to be, the H2O is going to be twice the amount of the N2O. So now we can solve for P(N2). So P(N2O), excuse me, that's plus, pardon me. Since that's 3, so if we get rid of that one, right, just add them together, you got 3. So this value is going to be equal to 2.63 divided by 3. So far, so good. 0.877 atmospheres. Now we can calculate what this one is, because if that's the part that's due to this one, then double that should be the rest of that 2.63. 1.75. 1.753 spheres. This is PNO2. This is PH2O. Right? Let's see if we add those together. 10, 12, 3, carry the 1, 6. Yep. Adds up to 2.63. So these are our values of partial pressure. Now we can plug them in here. So KP is going to be 0.877 atmospheres times 1.753 atmospheres squared. So I'm going to square that value sitting right there. And 0.877 times that. So this KP is equal to 2.696. Okay. We also want to know KC. So we need the formula for that. KP equals KC times RT to the delta N. RT to the delta N. Okay. We know what KP is. What's delta N? Well, in the temperature plus 273 equals 773 K. So what's delta N? It's after minus before. So after is 3, right? Minus 0. So delta N is 3. Okay. So instead of solving first, let's just go ahead and put in our values. KP is equal to 2.696. 0.696. And then that's equal to KC times 0.08206 for R, times T, which is 773. And all of this is to the third power. Okay. So let me go ahead and resolve this one right here. 0.08206 and 773 to the third power. This is 2.55 times 10 to the fifth. That means KC equals 2.9, excuse me, 696. 2.696 divided by divide that in 2.696. And I get 1.06 times 10 to the minus 5. Do better than that. There we go. So that would be the KC if we were to use molarity. Okay.
Instead of the H2O.
Oh, here went from here to here. The relationship between partial pressure of N2O and water is 1 to 2. So this would be, if this is this one, then that one is equal to 2 times this one. So I went from here to here, and I kept that one. And then I just said, okay, well, 2 plus 1 is 3. So I crossed that out and put a 3 in front of that one. Over here, okay, well, there's no gas on this side. So we've got a total of 3 moles here minus 0 moles gas, from the reactant side. Yeah, it's kind of busy up there. Could be hard to follow. That's the way it looks inside my head. All right. And one more. I think this is the last one. 36. At a certain temperature K for the reaction 2NO2 yields N2O4. The K for that reaction is 7.5. I don't know why they put units in there, because we never put units for K. If 2 moles of NO2 are placed in a 2-liter container and permitted to react, calculate the concentration of N2O4 at equilibrium. Okay, this one should be fairly straightforward. Gas in equilibrium with N2O4 gas, correct? Okay. And the K, K over here. K for this reaction is 7.5. Maybe since it's gases, they put liter moles in there so that we wouldn't mistake it for pressure. Something I can figure. But it's 7.5, and that would be equal to the concentration of N2O4 to the first power over NO2 to the second power. Okay, we're starting with 2 moles of NO2 in a 2-liter container. All right, so that's 1 molar. 2 moles and 2 liters. And we've got nothing here. So the change is minus 2x plus x. Because we've got to add here, subtract here. If we make this one the 1, x, this has to be minus 2x. So at equilibrium, we've got 1 minus 2x and x. Okay, am I missing anything? We're looking for the N2O4. Okay, so this one did work out well. All we have to do is find out what x is, and we got our answer. All right. So here we have 7.5 equals N2O4 is x divided by 1 minus 2x squared. And this is going to give us a quadratic. So we can either solve the quadratic or we can do successive approximations. With a K like that, this is going to be a substantial value, that x. Right? So we can't go with the first answer we get. If we let x go out and calculate x, then we're going to have to go back in and recalculate with that x. May have to do it twice to get the right x, and within 5% error. Or we can just do the quadratic and be done with it. So I think I did the quadratic in the worked problems. So let's do that so we can remember how to work quadratics. Okay. All right, so we got 7.5 equals x over what? Well, to expand the quadratic, remember, you have 2x squared, so that's 4x squared. And then we have 1 times 2x plus 2x times 1. So 1 times 2x is minus 2x. So we have minus 4x for the middle term. And then 1 squared is 1. Okay, so we bring that over to this side. I think I'll go this direction. 7.5 times 4. That should be 30. Yeah. So this one times that one is 30 x squared. This one times that one is minus 30x. And this one times that one is 7.5. 7.5. And that's equal to x. Are we good so far? 4 times that one. I just bring this whole thing over here. This is what I get out of it. 30x squared minus 30x plus 7.5. But x is still on that side. So in order to work a quadratic, we have to get everything on one side equal to 0. Okay. So this is plus x on that side. It's minus x on this side. So we're going to have 30x squared minus 31x plus 7.5 equals 0. Now this is A, this is B, that's C. And remember our quadratic? I'll just put the quadratic up here. So x is equal to minus b plus or minus square root of b squared minus 4ac all over 2a. So x is equal to minus b. So that'd be a plus 31. Plus or minus square root of b squared. So minus 31 squared minus 4 times a, which is 30, and times c, which is 7.5. Okay. And this is all over. All right. Okay. So let's resolve this in here. Since it's plus and minus is 2 possibilities, let's do this one and find out what this is right here. All the way down to the square root. So 31 squared. And then 4 enter and 30 times and 7.5 times. And that's subtracted from. There we go. So I get minus 8.69 times 10 squared. Does that look right? Let me do that again, because square root of a negative number gives you imaginary numbers, doesn't it? I must have done something wrong. Let me be sure I got it up here right. Okay. If this is b, that's minus 31. Yep. And then 4 times a times c. If I did that right. And then 2 times a. Yeah, okay. So let me try that again. 31 squared. And then 4 enter 30 times 7.5. Subtract. Nice. That's better. 61. Square root of 61. I must get the wrong key. So this resolves to 7.81. And now that's going to be 2 possibilities here. This one plus that value. Let's see. 31 plus divided by 60. This is one possibility. X is either 0.647 or 7.81 minus from 31. Divided by 60. And this is 0.386. So it's one of those other, one of the others of those. Which one makes sense? Well, if this is 0.647, then 2 times 0.647 is 1.3. Okay. And that would give you a negative number. Okay. So that would that. This one has to be it. Yeah, round it off, 0.39. Okay. Now we can, that's 11 o'clock. All right, go to 11:15. We can do successive approximations and just see how it works. Unless you're satisfied. Okay.